Let's start out with a more mundane topic, which is overloading. So some of our favorite languages support overloading, some more systematically than others. What is
Is the microphone on?
It doesn't sound like it's on?
No.
It's on? It is on? Okay, I can speak louder, I can move the microphone. Louder, all right.
Keep your head directly above the microphone.
Yeah, I don't think I want to do that. All right, well, if I get too quiet, somebody make a motion or something like that. All right. So why do we overload? It's in order to give an alternative interpretation or a variety of interpretations with a common vocabulary. It's nice to do that systematically. In other words, we don't give arbitrary interpretations, but we give interpretations that are related somehow in a classical way that we've been doing that for a very long time, is to have a collection of laws that are associated. So this is kind of the spirit of abstract algebra. Okay? Can we do something to bring the sound up, perhaps? Okay.
When you look this way, it's good. Yeah.
Oh, when I look at you, it's good, Robbie. Okay. Thanks. All right. So the laws give us a way to reason in a modular, reusable way. So that's wonderful. It's very powerful. We use it a lot. We also have another abstraction mechanism that we all are big fans of, I think, in this room, which is lambda. First-class functions. But these two mechanisms don't really go together. They're both very powerful, but they don't really go together. In other words, we can't really overload lambda. Okay? And so the most fundamental aspect of our programming language, which is the sort of what lambda variables and application, is not extensible. It always means the same thing, which is perhaps a shame. I think we're used to it, but it's at least interesting to wonder what would happen if we could extend it. Well, I don't know exactly how to do that. One could formulate some sort of language extension proposal and argue it, on IRC or something about it. But there's another way, which is just that we can eliminate these non-overloadable aspects of our language. We can transform them away. Okay? So there are a variety of computationally complete ways to talk about computationally complete calculi that don't have lambda in them. And I'm going to show you a transformation into one of them. So it's a quite simple transformation. So the lambda calculus has, 4 basic building blocks: constants, variables, applications, and abstractions. All right? So if we have a function, we can assume that, if we have that as an expression for a function, we can assume that it's a lambda. If it's not a lambda, we'll eta expand it, all right? So we just have to consider these 4 cases, and here's a simple translation. If we have lambda p some constant k, well, that's going to be const of k. So I'm not telling you what const means yet, but I'm going to rely on your sort of familiarity with some programming language that has something like it. If we have lambda p and then a variable, well, I'm going to assume that these expressions are well scoped, and so that variable has to be p itself. So we have another name for lambda pp, which is the identity. So these first 2 transformations have eliminated a lambda each. That's good news. The next one, if we have lambda p and an application, what can we do? Well, we can break up that expression into lambda p, the function part, u, and lambda p, the variable part, v, right? Those are also going to be well typed and well scoped, and we can transform them. Well, what do? Well, once we have those 2 functions, we can we can combine them into a single function that generates the pair of the function and its argument, the u and the v, and then later it does an application. So again, I'm not telling you what this combining operation. I'm taking a notation from Jeremy Gibbons' paper, Calculating Functional Programs, which I like very much. So he has this operation, he calls it fork there. I think it goes by a variety of names. So here we're combining the 2, and then afterward doing an apply. Okay, so this is how we can get rid of, this is how we can move a lambda into an application. Next, if the body of the lambda expression is another lambda expression, well, we can syntactically uncurry it, all right, and then curry the result. So all I've done is curry of uncurry, but the uncurry is kind of invisible here because I've applied it syntactically. Well, I'd really like to use a simple sort of lambda calculus that doesn't have patterns, it just has variables. Okay. So really what I would do is curry lambda r, some other thing, and then wherever I see p, replace it with first of r, and q replace it with second of r. So it's a very simple transformation. And now we've eliminated all lambdas, okay, and variables and applications. Well, some things you might call application, like these operators here, but I mean, there are no kind of general applications. Now, you could do this manually, and it might be fun the first 1 or 2 times you do this on some of your favorite lambda expressions, but it would get old. and it's not a pleasant programming interface, okay? It's not a pleasant programming interface to use just the vocabulary on the right, and it's not a fun process to do very many times to make the transformation from left to right. But we can automate it, and in particular, we can automate it with the compiler plugin. Okay, and that's what I'm suggesting. Whoops, wrong direction here. There we go. So here's some simple examples. Top half of the slide, we have some simple Haskell definitions. And the bottom half of the slide, we have the definitions, exactly the same meanings, but transformed into this lambda-free vocabulary. All right, so you can see there's function composition, there's this fork operation that glues functions together, and then there's some funny named primitives here, multiplication and addition. Okay. Now, what are these operations? Where do they come from? Well, the idea is to give alternative interpretation. So I'm going to want to give an interface that describes these functions and some laws for them, these operations, and then a variety of interpretations. So that's what we do next. So what is an interface for function-like things? Well, unsurprisingly, it's categories. Categories and some specializations. So I'm not going to go through these in detail. I'll give you a flavor. Some of you already know what these are. Some can read in the paper. So we have the idea of a category, which is identity and composition, and it has 3 laws. Next, we're going to need products. Okay, so products come with 2 eliminator forms that project out of a product, and then 1 introduction, which is exactly this fork operation that takes 2 functions and gives you a single function that generates a pair. The 2 functions you give it have to have the same domain. And again, we have laws. Okay? And then there's a dual to products, coproducts, which show up in Haskell as sum types, in ML, other languages. And the operations are exactly the dual. So if you look, all that's happened here is products become coproducts, so products become sums or coproducts more generally. And all the arrows are reversed. And if you look at the laws, they also are just exactly reversed. The forks become joins, the compositions get swapped around. So that's coproducts. And then there's exponentials, which is like first-class functions. And here we have apply. That's where the apply came from in the previous slide. And we have curry and uncurry, and they're also a set of laws. Okay? So this is a very well-explored set of interfaces and laws. This is category theory. Okay. Well, we need a little bit more, which is the primitive operations, things like addition, multiplication, sine, cosine, that sort of thing. Okay, and thus although these operations are overloadable in Haskell, for instance, they're not overloadable enough because they always mean functions, and I need some other function kind of a thing. All right. So where are we? We've eliminated lambdas, variables, and application. Okay, those were the kind of inconvenient things that we couldn't overload. We've replaced them by vocabulary that's overloadable. Okay. Now let's do some overloading. All right. So one of them is just the function instance. So every one of those classes I showed you has an instance for regular old functions. If you use that instance, we get back the usual interpretation of functional programs. So let's do something else instead. All right. So here's an example. I showed this code before. This is magnitude squared of a pair, which is just the sum of the squares. Okay. The second line here is the translation into the categorical vocabulary. And the third one is a graph. Now this picture is the compilation of this code. Okay, so this is the idea here. You write this code, the plugin translates it to this form, and then that form is now more polymorphic. It no longer just describes functions, it describes all kinds of things. One of those is the graph category, and this is the graph that shows up. Okay, really this is a picture of the graph. Right? The graph is an underlined representation. This is a picture of it. Okay, here's another one. And here's another one, and this one's has a wrinkle in it, which is it has currying. Okay, there are a variety of ways that one might try to visualize a curried function or higher order functions in a graph. This is the one I picked. Okay, so this is the lambda x here. That's the lambda y here. And this is 3 plus y. Good, that shows up. Plus x, or x plus that. Okay. Now, as I said, this is just this picture is a picture of the graph. So the graph is rendered into a picture, but it can be rendered into other things. Jumping ahead of myself. So I said this graph comes from another interpretation, which is just another instance of these classes. All right? And these classes often have fairly simple instances. And this is the essence of the graph, of the implementation of this graph category. It's not all of the code, but it's sort of all of the interesting code. There's just a very simple monad in here, this graph M. That graph M is just a state monad that keeps a counter and a collection of components. And those components are exactly these things, like the ins and the multiplies and so on. So it's quite simple. And if you look at the category instance, this is as simple as you might imagine it to be. All right. Here's another example of graphs. So this is a type I showed yesterday. 2 to the 4 just means a binary tree of depth 4, a top-down binary tree of depth 4. This sum is the sum function from the standard Haskell library, from data.foldable, I guess, where this is. Okay? So it's not like I had to write some funny sum. This is the usual sum function. This picture I showed in my talk yesterday. This is a parallel scan. And yesterday I mentioned in my talk, somebody asked about automation, in particular the pictures, and I said I'll show you tomorrow. So the way I generated the pictures in yesterday's talk was I compiled the Haskell code I showed you into those pictures. Okay? So one piece of code, usual interpretation gives you Haskell, another interpretation gives you this graph form, and I'm rendering that graph form right here. All right. Here's another example, Bytonic sort. And of course, this can be as large, right? So I've done a Bytonic up to, I don't know, maybe 6, which is 2 to the 6 number of elements. It gets more and more complicated looking, but I'm confident that it's correct because it's very, very simple code. All right. Now, so the category is a category of graphs that got generated. I rendered it into some pictures that I showed you. You can render it into other things, like Verilog code. And this was the original motivation of this project, is compiling Haskell to hardware. So when I compile Haskell to hardware, it's translate the Haskell into this categorical form, the CCC form, and then use the graph category, that interpretation, and then render that graph into Verilog. And that last step is quite simple. Both steps, the graph construction and the graph rendering, are quite simple. This is another rendering of the same category. I'm going to show you other categories, but just to show you that some of them are reusable. So here we have a very simple graphics language. The idea of an image, or here is even more simply, a region is simply a function from R2 to bool. Okay? So it just means if the function is true, then we display black, and if it's false, we display white. Okay? And here's a very simple animation. This is the disk function takes a radius, and it gives you a region. That region is a function from a point P, and it simply says, is the magnitude of P less than or equal to R? Well, for efficiency, I'm saying is the magnitude squared of P less than or equal to magnitude less than or equal to the square of R. And here's a very simple animation. Okay, this is the graph. I can render it to the graph, but I can also render it into GPU code. This is GLSL. It's a bit of old school way to do GPU code, but it runs on your phone, which is kind of cool. And there we go. This was not in the paper. So this is the code I just showed you. Generates a GPU code. This is running on GPU massively in parallel on this machine. Well, however, this is a like 3 or 4-year-old machine here. Okay, and a little bit more complicated, but still not very much more complicated bit of code, and generate more interesting animations. Okay, so all right. Here's another category, the category of differentiable functions. All right, so. It's not possible, it's not computable to take a function and differentiate it. Exactly, of course, I don't mean approximately, exactly. That is from the outside of function. But we can take the impossible and make it easy by saying, instead of functions that we're going to differentiate, we're going to build differentiable functions in the first place. And how do we build them? Well, we need a representation. And the simplest possible thing I can think of is a differentiable function is a function that constructs not only the usual result value, but also its derivative. Okay, so in other words, just put the answer into the representation. Well, that seems like it's cheating, but that's not the whole story. Now we have to build up differentiable functions using a vocabulary that knows how to how to combine the forms. So the identity, composition, and so on. And it's quite simple. This really is the code. This is just a pretty printing of the source code here. Okay, so for instance, the category instance says, well, what's identity going to be? All right, well, what is the derivative of the identity function? Well, you might say it's 1, but That's only true for scalar functions. It's not even true for scalar functions. In general, the notion of a derivative is a linear map. So that's what we have here. So a function from a to b, the usual value, and a linear map from a to b. That's the kind of very general notion of a derivative. And for every linear function, it is its own derivative everywhere. That's just a property of a linear function. So when we say 1, we really mean the identity function on scalars. All right? And this is the chain rule. It's quite simple. Okay? For Cartesian, so the chain rule is about sequential composition. This fork operator is really about parallel composition. It looks very much like the chain rule, but it has less dependence in it. And then for each primitive, we say, well, negation and addition are linear, so they're quite simple. Multiplication is, well, it's going to compute multiplication, but also its derivative using the product rule. And that's pretty much all there is to it. Okay. Now, for fun, we can combine interpretations. So it's not just we can give, you can choose from one of many interpretations, you can actually combine them. So what if we take our function magnitude squared, and here I'm showing the graph interpretation, but what if instead I give the derivative interpretation and then the graph interpretation of that, I mean the differentiable function, and then the graph of that, and we get this. Okay? Here's another one. Now, if you're looking closely, you'll see the size of the output is getting bigger. That's because these are all the partial derivatives here. And this one has 4 partial derivatives because the function from R2 to R2. Okay. So another example is something called interval analysis. Interval analysis is this technique that instead of mapping, so a function from A to B, instead of taking a value of type A and returning a value of type B, you take a whole collection expressed as an interval of values of type A and get a whole collection of intervals of type B. And the promise is that the result interval will contain the result of applying the function to every one of the elements of the input interval. And it's extremely simple to write down. Okay. And there's a picture of the graph of the interval analysis interpretation of this function down here. Okay. There we go. The paper contains some other examples. Some of these are maybe not in the paper but mentioned. One of them that I just like very much, this was suggested by John Wheatley. John Wheatley had picked up this compiling to categories and was going to do a project, but then he had this wonderful idea, which is we have SMT solvers. They're very powerful, do wonderful things, but they're awkward to use. If you're lucky, you'll find some nice monadic interface, okay? But the idea is, what you need to say when you give one of these constraint problems is simply a function to bools. Haskell already is a perfectly nice language. It's not a limitation of the language, it's a limitation of the compiler, okay? So there's a fairly simple category for SMT solving that just drives the SMT solver. Okay, linear maps themselves from a category. Incremental evaluation, this is quite fun. The differentiable function example I gave you, I didn't point it out at the time, but the only operations that were needed for the category instance is that linear maps is a category, and the only operations needed for the Cartesian one is that linear maps are Cartesian. And so you can actually generalize and put any Cartesian category in there. One of them gives you incremental evaluation. Okay. All right. Oh, am I going backwards here? There we go. All right. I think that's a good place to stop. Questions?